If we think back, guys, to last week, we started talking about the development of our current model of the universe. And that started with Aristotle way back in the 5th century BC. Aristotle came up with this thing that we call the geocentric model of the universe. The geocentric model of the universe, coming from the word geo means earth, earth-centered model of the universe. In other words, the sun, all the planets, all the stars, everything revolves around the earth. And we talked about this being not so far-fetched. If we were to look up in the sky and not know any different, then we'd probably think that the earth is the center of the universe as well. We now know it's not, okay, but it doesn't seem so far-fetched that back in the 5th century BC, 2,500 years ago, somebody might think that. Let's fast forward a couple thousand years to Copernicus. Copernicus comes up with what we call the heliocentric model of our solar system. Helio means sun, the sun-centered theory of our solar system. In other words, the sun is the center of our solar system. All the planets, including the Earth, revolve around that sun. It doesn't tell us how they revolve around the sun. It doesn't tell us why they revolve around the sun, just that they do revolve around the sun. Let's fast forward a little bit further. We had a guy named Tycho Brahe. He was the pea guy, remember? He was the guy that held his pea and died because of it. Tycho Brahe made some naked eye observations of the stars and of the planets and of the sun and measured angles and measured times and measured distances and so on and so on and so on, and that's pretty much where it ended. His assistant's name was Johann Kepler. Kepler, after Tycho Brahe died, took some of that data and then formulated 3 laws. 3 laws that describe not only the motion of the planets, but how the planets made the motion that they did. In other words, how the planets revolved around the sun. The first one was the Law of Elliptical Orbits. The Law of Elliptical Orbits said that the sun stays where it is. The Earth and all other planets revolve around the sun in an elliptical path, but the sun's got to be at one of the focal points of that ellipse. So in other words, the sun maintains its position, the Earth and the other planets determine their orbits such that the sun will be at one of the focal points of that ellipse. The second law that Kepler came up with that described the motion of the planets was the law of equal areas. And the law of equal areas says that a line that joins the sun to the Earth, or the sun to any other planet for that matter, sweeps out equal areas in equal time intervals. The third law, the law of periods. The law of periods says that the square of the period of revolution of the Earth or any other planet around the sun is equal to, or is proportional to, the cube of the average radius of revolution of that planet around the sun. In other words, there's a constant called Kepler's constant for each different object being revolved around that is equal to t squared over r cubed. And that allows us to find data about one planet using data about another planet, okay, and what it orbits around. Finally, this is the last thing we've been talking about. We've got Newton. This guy told us that the Earth revolves around the sun. This guy told us how the Earth revolves around the sun. This guy told us why the Earth revolves around the sun. Why does the Earth revolve around the sun? Yeah? Gravity. Gravity is that force that acts between any 2 objects with mass, including the Earth and the sun, including the apple and the Earth, including you and your neighbor. Any 2 objects with mass exert a force of gravity on each other. Now, Newton derived an equation for that force of gravity. Looked something like this. Well, it looked exactly like this. F is equal to g m1 m2 over r squared. G was a constant. Okay, its value, 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. We call it a universal constant. It's a universal constant because it never changes anywhere in the universe. It's 6.67 times 10 to the minus 27. If we're trying to find the force of gravity between you and you, it's 6.67 times 10 to the minus 27 if we're trying to find the force of gravity between you and the Earth. It's 6.67 times 10 to the minus 27 if we're trying to find the force of gravity between 10 to the minus 11, I should say, sorry, between the Earth and some star, not the sun, but some star in a far-off corner of the universe. It's always the same value, so we call it that universal constant. M1, M2, they're the two masses that are involved. Doesn't matter which is which. Okay, make sure they're in kilograms. R, we think of as a radius often because, okay, it looks like it should be radius where it's R. Okay, but in the end, R is simply the distance that separates the centers of the two objects. So we're trying to find the force of gravity between two people over here. Okay, it's the distance between the center of U and the center of U. We're trying to find the force of gravity between the Earth and the Sun. It's the distance between the center of the Earth and the center of the Sun. We calculate that force of gravity. When we do that, we're always going to get a positive number. And that's why we have these absolute value signs around it. It indicates that we can't get a direction with it. There is a direction. Force is a vector. Its units are newtons. There is a direction. But we're not going to determine the direction by the equation. We've got to figure out the direction some other way. But you know what? That's easy, because we know it's always going to be an attractive force. So if the Earth is right here, and the apple is right here, not drawn to scale, by the way. Otherwise, that would be a really, really big apple. And then the apple experiences a force to the left. Hey, what direction does the Earth experience a force? To the right. Which force is bigger, the force on the apple or the force on the Earth? They're the same force. If object A applies a force on object B applies an equal and opposite force on object A. So why does the apple fall towards the Earth and the Earth not fall towards the apple? If this thing experiences the same as force as this thing, then why does this thing fall and this thing not fall?
That could be debatable, but the reference, if your point of reference is the Earth, the apple falls towards the Earth.
Well,
way less
yeah.
Way less.
Yeah. It does depend on what frame of reference you're using, right? It's a good point, Rucker. From the normal frame of reference, we would say that the apple is accelerating towards the Earth because it's lighter, right? But if you actually use the accelerating frame of reference, okay, the apple is the frame of reference, then which one's accelerating? The Earth is accelerating towards you then, right? Okay, but we're not going to get too deeply into that, I don't think. Good? All right. We had some questions for homework on page 209, but these questions were a little bit more complicated than just F is equal to gm1 m2 over r squared. These ones had three objects in a row: the Earth, the Moon, and the Sun, all in a row. We wanted to find the force of gravity on one of these objects, in this case, the Earth, due to the Moon and the Sun. How do we tackle that? How do we tackle that? How do we find the force on the Earth due to the Moon and the Sun? Josh? We got to add the two together. But you know what? Listen, we got more than one force. You said we got to add the two forces together. Whenever we have two or more forces, we've got to first draw a free body diagram to show the direction. So let's draw a free body diagram showing the force of the Moon on the Earth and the force of the Sun on the Earth. The force of the Moon on the Earth is to the right. We're going to call it FME, the force of the Moon on the Earth. The Moon pulls the Earth to the right. Now, in the end, the Earth pulls the Moon to the left, right? Why do we not draw that in? I'm going to erase that. Why do I not bother drawing that? Because it's already what? Not exactly. Not exactly. Why do I not care about the force of the Earth on the Moon? Yeah, what are we trying to find? We're trying to find the force on the Earth. Is there a force on the Moon? Sure there is. I don't care what it is because that's not what I'm asked to find. So don't bother cluttering up your diagram showing forces on things that don't matter. They're there, but they don't matter because we're not trying to find it. So let's draw the force of the Moon on the Earth, and let's draw the force of the Sun on the Earth. Now, we don't know what the values of either of those forces are, so it doesn't really matter how long we draw those forces. Remember, there is a force of the Earth on the Sun as well, but again, we don't care what it is because we're not trying to find that force. Let's get those two magnitudes now, those two values. The force of the Moon on the Earth is equal to G times ME, MM, over R squared. 6.67 times 10 to the minus 11 times the mass of the Earth, which was 5.97 times 10 to the 24, times the mass of the Moon. Now, I don't remember what the mass of the Moon is. It's on your data sheet, though. Somebody want to check that for me? What is it?
Actually, we did these questions one page before, an example. We did the exact same question, the exact same distance, except we're going to
Right, yeah, that's right, yeah. Well, what is the value of the mass of the moon? 7.36 times 10 to the 22. 7.36 times 10 to the 22 kilograms, thank you. And we're going to divide that by r squared. What's the distance from the Earth to the moon? We don't need to look that one up because it's right there, right? 3.84 times 10 to the 8 meters. Now don't forget to square that, okay, inside the brackets there. Let's open up our calculator. Make sure we can all do this. Yeah, let's say 6.67 times 10 to the negative 11 times 5.97 times 10 to the positive 24 times 7.36 times 10 to the 22. Let's get that number on top there. Okay, 2.9 times 10 to the 37. Let's divide that by some brackets here. 3.84 times 10 to the 8. Let's end that bracket. Now let's square that whole term. We're going to get 1.9875 times 10 to the 20. That's a big force. That's a really, really big force. But that shouldn't be overly surprising to us. The force of gravity to the moon and the Earth is going to be huge because the masses of the Earth and the moon are so huge. And in the end, you got to think about why the Earth revolves around why the moon revolves around the Earth. It's because of gravity. If gravity is big enough to keep something that has a mass of 10 to the 22 kilograms in orbit around the Earth, then it's going to be a pretty big force. Let's calculate the force of the sun on the Earth now. FSE. G times MS ME over R squared. The mass of the sun, I think, is 1.99 times 10 to the 30. Is that right, Brennan? The mass of the Earth is 5.97 times 10 to the 24. And then we divide that by the distance squared, 1.50 times 10 to the 11. Now, my prediction would be that the force of gravity between the Earth and the sun would be larger than the force of gravity between the Earth and the moon. And I predict that for a couple of reasons. One, because look, the Earth is heavier and it has to orbit around the sun, so it's going to take a pretty big force. Bigger force, you would think. Secondly, the sun is so much more massive than the moon. You'd think it's going to provide a bigger force. But the thing that counters that is the distance. It's a much bigger distance as well. So maybe that's going to give us a smaller force. We'll see. What do you get when we multiply all those numbers together? Anybody have that? 3.52. Let's keep going then. Oh, but let's keep going with, okay. Let's get a few more decimal places there. Let's say 6.67 times 10 to the negative 27 times 1.99 times 10 to the 30 times 5.97 times 10 to the 24. Let's divide that by 1.5 times 10 to the 11. And square it. 3.5218 times 10 to the 22. Is it? Now what do we got to do with these? So what do we got to do with these? We got to add them up. Are we going to make one of them a negative? Why not? Both positive? Brendan, why are they both positive? Yeah, yeah. And you can see that the direction of the force, according to our free body diagram, they're both to the right. So let's just add them up. Let's say net force is equal to FME plus FSE. Let's make them both positive. We add them up. We get 3.54 times 10 to the 22. Is that good? How many people got that question? Okay. I think we should be good with that. On Monday, I told you we were going to have a quiz on Tuesday. Obviously, we didn't have a quiz on Tuesday because we weren't here. On Wednesday, we did our activity. Today, I didn't want to just spring that on you because I didn't think to mention it to you yesterday. So we will have our quiz tomorrow. The quiz on Tuesday, though, was supposed to be on Kepler's laws, and that was it. Tomorrow's quiz will be on Kepler's laws, but also on Newton's law of universal gravitation. So we'll just make it a little bit bigger than we would have made it on Tuesday, okay? So be prepared for that. Kepler's laws is basically the stuff that we reviewed here today and the stuff that we did here today. We're going to take a quick look now at question number 2 for those of you who did try question number 2, but you don't need to worry about something like that on the quiz tomorrow, okay? Up to question number 1, fair game. Question number 2, just kind of exercise for the mind here. Yep. Yep. Oh, I did that again. Should be 6.67 times 10 to the minus 11. Thank you. That doesn't change our answer down there because it was 10 to the 22 with that number. It would have been not 10 to the 22 with 10 to the minus 27 there. But you know what it is? You know why I get that mixed up? Because in physics 30, we use a charged particle called an alpha particle a lot. And an alpha particle has a mass of 6.65 times 10 to the minus 27. So it's almost the same base, but it's a different exponent. So, yeah, I don't know. For whatever reason, I mix them up a lot. Good there? Can I erase that stuff so I can take a look at? Actually, I don't want to erase that stuff. I don't, because my numbers are going to be a lot the same. Actually, let's just extend this page and finish up question number 2. Question number 2. Anybody want to suggest what I'm going to do with that? How many people got it? Okay. Josh, what do you do with that? Yeah, we still got to draw a free body diagram, right? Then we solve it as a vector diagram. The force of the sun on the earth is this way. The force of the moon on the earth is this way. And you know what, guys? We know the values of both of those because we just calculated them. The distances are the same. The numbers are all the same. This one's going to be 3.5218 times 10 to the 22 newtons. And this one is going to be 1.9875 times 10 to the 20 newtons. Now we want to find, we've got to add them up. We want to find the sum of those, though. We're going to add them up like this. FSE, which is 3.52, FME, which is 1.98. How do you find this net force here? You want to find a net, it's always adding. But if it's two-dimensional, then you got to add them using x's and y's like this. So what are you going to do? Yeah, it's the Pythagorean theorem, and then you're going to find the angle by doing the inverse tan function. How many people got question number 2? Okay, good. All right, you had a little bit more homework on page 683, number 1, 3, 4, 5, and 6. Any issues with any of those questions? Wayne? 5? Yep, 6. 5 and 6, any others? No? All right. Question number 5 says Mars has 2 moons, something in Phobos, Deimos and Phobos, each named after an attendant of the Roman war god Mars. Deimos has a mass of 2.38 times 10 to the 15, and its mean distance from Mars is 2.3 times 10 to the 7. Phobos is this mass and this distance. Without doing any calculations, which moon will exert a greater gravitational force on Mars? And let's explain the reasoning here. Can anybody give me that answer? Yeah? Closer and more. It's bigger and closer. Okay, so yeah, so if we look at the equation, GM1M2 over R squared, What gives us a bigger force? Well, bigger mass gives us a bigger force, right? We know that, right? The force of gravity between an apple and the Earth is much greater than the force of gravity between an apple and you because the mass of the Earth is much bigger than you. So bigger mass, bigger force, okay? The force of gravity between you and the Earth is a certain value right now. If you were at the International Space Station, it would be much lower because the distance is greater. The smaller the distance, the closer it is to the object that's producing the gravity, then the bigger the force is going to be. So which one was it? Phobos? Phobos because it has the bigger mass and the closer distance. Bigger m, smaller r. Check your prediction in part A by calculating the magnitude of the gravitational force exerted by each moon. Mars's mass is this. Let's just show the basic idea behind this. I think you can do the calculations yourself here. Okay, we want to find the force between, let's say, Phobos and Mars. It's going to be 6.67 times 10 to the minus 11 times the mass of Phobos, which is 1.1 times 10 to the 16, times the mass of Mars, 6.42 times 10 to the 23. Mass of the moon and the planet. The distance is 9.4 times 10 to the 6 meters, and we got to square that. Okay, we'll get a number there. I'm not sure what it is, but it's not very hard to calculate. If we want to do the other one, it's going to be exactly the same thing, right? Except I'm going to switch this number, the mass of the moon, and we're going to switch this number, the distance from the center of the moon. Okay, is that good? Who asked me for that question, number 5? Is that good? And number 6. Suppose the equatorial radius, let me copy this one over as well so we have more space to work with. Suppose the equatorial radius of the Earth was the same as on the moon, but the Earth's mass remained the same. The moon has an equatorial radius of 1.74 times 10 to the 6. That's the distance from the center of the moon to the surface at the equator. Earth's mass is this value, and its equatorial radius is this. What's the gravitational force that this hypothetical Earth would exert on a 1 kilogram object at the surface? Well, we're going to say that F is equal to G m1, m2 over r squared. It's 6.67 times 10 to the minus 11. Times the mass of the Earth, 5.97 times 10 to the 24, times the 1 kilogram object, divided by the equatorial radius here, which, remember, we're not using the equatorial radius of the Earth. We're using that of the moon, 1.74 times 10 to the 6. And we got to square that. Okay. I don't know what that value works out to be, but you can find it, right? You get the value of that force. Now, what does B say? How does the answer in part A compare to the actual gravitational force exerted by Earth on this object? Bless you. For B, you want to find the actual value by using the same equation, but with the real radius, not with the radius of the moon, but the radius of the Earth. And then we want to compare them. How many people in here, how old are you guys? 15, 16? Some of you guys are probably 15, some of you guys are 16. Who's 16? Okay, probably about 3/4 of you. Let's pretend I'm 40 for a second. You know what, let's make me feel even better about myself for just a moment here, okay? Let's pretend I'm 32. I'm not, and it's been a couple of years since I've been 32, but let's pretend I am. Let's compare my age to your age. You're 16, I'm 32. Let's compare my age to your age. What's the comparison? Somebody tell me the comparison of my age to your age. I'm twice your age? How'd you figure that out? Yes? Or we could say 32 divided by 2 is 16. So I'm twice your age, right? We want to compare two numbers. Let's divide them. Let's compare my age to your age. 32 divided by 16 is going to be 2. I'm twice as old as you are. Right? If we want to compare these two forces, the force in question A, the force in question B, then let's divide the force in question A by the force in question B. Okay, we calculate that force easily. We calculate this force easily. Let's divide the two. Okay, I don't know what we get, but that's going to be our comparison. If we get a number that's 3, then we're going to say it's 3 times as much force. If we get a number that's 0.25, then we say it's 0.25 as much force, or 1/4 as much force. Okay? Who asked me for number 6? Okay? You're going to do that quite a few times in Physics 30, Jace, is compare. You see compare, find a ratio. They all mean the same thing. Okay, as soon as you see those words in Physics 30, particularly, the thing that I want to come to your mind is divide every single time. And again, you think back to that example of, compare my age to your age. Okay, everybody, probably every single person in the room was thinking, oh, he's twice as old, right? But in your mind, in the back of your mind somewhere, you all divided 32 by 16 and got 2. Okay, so let's do the exact same thing here. The only difference is we're dealing with numbers that aren't as convenient as 32 and 16. Right? Okay. I want to spend a quick moment just before we move on something that we call the torsion balance experiment, which is just an experiment that was performed by a guy named Cavendish, not by Newton, a guy named Henri Cavendish, to determine what the value of G was. Now, Newton came up with the law, F is equal to gm1m2 over r squared, to describe the force of gravity that exists between two objects with mass. But it wasn't Newton that came up with the value of that constant. Newton knew there had to be a constant G. He just didn't know what its value was. Cavendish figured that out. Cavendish set up an experiment that looked something like this. You got a string hanging from the ceiling. On the end of the string is this little rod. On the end of each of those ends of the rod is a mass. We're going to call this mass 1, and we're not even going to label the other one. The other one will be the same value as mass 1, just so that it balances, basically so that it doesn't tip over. Okay, but it's not really important in terms of the experiment other than making sure that this thing balances it. Right, Aiden? This string has certain torsional properties or twisting properties. That's what torsion means, twisting, rotating properties. You guys have all been on a swing set before. When you're on a swing set, especially when you're little, this is what you want to, it seems to be always what you want to do. Okay? First of all, you want to go as high as you possibly can. Your goal when you're a little kid is to always seem to want to swing all the way around, right? Let's see if I can swing all the way around and do a loop around. You can't do that.
Unless you have rock.
Okay. Okay, unless you have, thank you, unless you have rockets strapped to your back, yes. Normally, Rucker, you can't do that, right? You can't go all the way around. And you guys know why now, right? You guys know the whole idea of vertical circular motion. You can't go all the way around there because there's a certain minimum speed that you have to be going. And when you're just pumping yourself back and forth on that swing set, you can't get going that minimum speed. There's no way that you can get yourself going that minimum speed necessary to go all the way around the loop. So you can't flip all the way around. Okay? But the other thing that you always seem to want to do, especially as a little kid, is to twist it up, twist the chain up so that you can kind of let yourself go and spin and spin and spin and spin. And you guys know that the more you twist it, the more force that takes, the harder it is to twist it. Right? The more it's twisted, the more difficult it becomes. Now, you don't know what the exact value of the force is that's required to twist it 1 revolution or 2 revolutions or 3 revolutions, but you know that the value of that force increases. You could measure how much force was required to twist it 1/4 of a revolution or 1/2 of a revolution or 3/4 or a full revolution. You could measure that force. If you did, you would measure the torsional properties of that swing set, the twisting properties of that swing set. Now, Cavendish would have measured the torsional properties of this string. He would have known how much force was required to twist it 1/4 of a revolution or 1/2 of a revolution. He would have known how much force was required to do that. He used that to determine the value of the force that was acting when we brought mass 2, which I'm going to represent by my fist here, mass 2 near mass 1. So mass 2 is coming near mass 1 right now. You can see the shadow on the smartboard right now. Object number 1 will be attracted towards number 2. Now, it's going to be a really, really small force of attraction, but it's going to be, nonetheless, a real force of attraction. It's going to be attracted towards it. It's going to move towards it a little bit. We can measure the value of both of those masses. M1, which you see on the board there right now, M2, which is represented by my fist coming near it. We can measure the value of R. That's the distance that separates M1 and M2. Use a ruler. And we can measure the value of the force by the torsional properties of the string, the twisting properties of the string, just like the twisting properties of the swing set. Okay, the twisting properties of the swing. We get the force. If we know F and R and M1 and M2, and Cavendish did, then he was able to solve for the one thing that we didn't know up until that time, and that was G, the gravitational constant. So it became equal to F times R squared over M1 times M2. Does that make sense? It's a simple experiment. In theory, it's a simple experiment. Now, to actually do it, it's a lot trickier than it might seem because the value of the force that acts between M1 and M2 is going to be a really, really, really small value. So this, and really hard to measure. But this is a bit of a simplification of what he did, but in essence, it's what he did. He measures the value of M1, which you see right here, M2, which is represented by my fist. Okay, bring it nearby, M1. He measures both of those. He measures the distance that separates them, R. He measures the value of the force by looking at how much it twists, and then he simply calculates the value of G. What did he get? Go figure 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. Good? Okay, let's move forward here. Today we're going to move forward to our second to last topic of the unit, gravitational fields, which means that we're going to have a unit test coming up relatively soon. I was going to mention this to you yesterday, and it kind of slipped my mind. We're going to have a unit test coming up on Tuesday of next week. So it's only 5 days, but you had a good weekend to study for that. Okay, gravitational fields. What's the deal with gravitational fields? Sounds a lot like gravitational force. Not the same thing. A gravitational field is an influence. Let me explain that. It's not a force, it's not a push or pull. It's an influence. Right now I've got the smartboard marker in my hand. Okay? It experiences a force of gravity caused by what? Caused by what? Yes, you're right. Actually, you're right. It's not what I was looking for, but you're right. Okay, I was thinking caused by the Earth, right? But there is a force of gravity caused by everything. Okay, the biggest force of gravity is clearly caused by the Earth, though. And it's pulling downward, right? That force of gravity is there. This pen is being pulled down toward the Earth because of that force of gravity. Push or pull, it's being pulled down toward the Earth. What if I take that pen away? Now it's gone. It doesn't exist anymore. Is there a force of gravity at that spot where the pen was? Okay, here's the Earth. Here's the pen. There's a force of gravity acting on it. If I take away that pen, it's gone. There's nothing there now. There's not even any air for whatever reason. There's nothing there. Is there a force of gravity there? No. Force of gravity is a push or a pull. In order to have a force, you need to have something to be pushed or pulled. You can't push or pull nothing. In order to have a force, you need something to experience the force. You need something to be pushed or pulled. Does that make sense? There's no force of gravity there. Does that mean that gravity has disappeared? Does that mean that the Earth doesn't make gravity anymore? The Earth makes gravity no matter what. Remember we talked the day we introduced this. I think some of you were gone at band or something, but the day we introduced this, we talked about the curvature of space-time, Einstein relativity. Remember we had the blanket here, We put a big rock in the middle of the blanket, it dents the fabric of space-time. Put a marble in the corner, it rolls towards it. That's why there's a force of gravity. If we take away that marble in the corner, the rock in the middle still dents the fabric of space-time. The Earth still dents the fabric of space-time. Gravity doesn't disappear because the pen disappears. Just the force of gravity disappears because the pen disappears. So there's still something there, but it isn't a force anymore. That something that's there, we're going to call a field. It's an influence, but it's just not doing anything right now. Does that make sense? It's the curvature of space-time. It's the influence of gravity that just isn't influencing anything right now. That just isn't pushing or pulling anything right now. A field is a line of influence that surrounds something. There's lots of different kinds of fields. There's gravity fields, there's electric fields, there's light fields, there's heat fields. Specifically, we're talking in this unit about a gravitational field. It's a line of influence that surrounds an object with mass. It shows us the influence of gravity, even if we don't have anything being influenced, even if we don't have anything experiencing it. In order to have that field, we need a producer. We need something to cause it. We need something to dent the fabric of space-time. The big rock in the middle of the blanket, the Earth in the middle of space-time. Now, to have a field, you need a producer. To have a force, you need an experiencer, something to feel the field. To have a field, all we need is the Earth. To have a force, we need the Earth and the smartboard marker to experience the field. Now, just like with other quantities like forces and velocities and accelerations, we still distinguish between vectors and scalars. Some fields are vector fields, some fields are scalar fields. In other words, some fields have a direction associated with them, some don't. Gravitational fields are vector fields. They influence things in a direction. The board marker experiences the gravitational field so that the board marker will move down. The board marker will never move up because of gravity. It'll always move down because of gravity. All masses experience a force in the direction of the field, never against the field. Hence, the direction matters. It's a vector field. There are two equations that describe gravitational fields. They're going to look, the first one at least is going to look real similar to one of the equations that we've already seen. G, the gravitational field, is equal to big G times m over r squared. This is the gravitational field strength. Caused by something, caused by a producer. And the units for gravitational field strength would be newtons per kilogram. G, we know what big G is, right? It's that constant 6.67 times 10 to the minus 11. It's still the same thing. M is going to be the mass of the producer, the mass of whatever caused the field. And that's going to be in kilograms. And R is going to be the distance from the center of the producer. You want to find the field strength 100 meters above the surface of the Earth. Then let's use big G, the mass of the Earth, and then the distance from the center of the Earth to that point 100 meters above the Earth. Notice we didn't say anything about the board marker there experiencing the field. When we use the producer equation, we don't need to know about the experiencer. There may not even be an experiencer. It doesn't matter. We just need to know information about what caused the field. There may be something experiencing it. There may not be something experiencing it. It doesn't matter. If, however, we use the other equation, which is the experiencer equation, then we need to know something about the experiencer, not the producer. So this one would be, let me change the color of this one actually. This one would be the gravitational field experienced by a mass. And the units would be the same. Still going to be newtons per kilogram. This is going to be the force of gravity experienced, or in other words, the weight of the object. Talking about the board marker now, right? The gravitational field experienced by this board marker is equal to F over m. F is the force experienced by the board marker, and m is the mass of the board marker. So which one do we use in a given problem? Depends. What do you know more about? If you know more about the producer, use the producer equation. If you know more about the experiencer, use the experiencer equation. If the board marker is a certain distance above the Earth, and you know something about the Earth, then use the first one. If you know something about the board marker, then use the second equation. If you know something about both the board marker and the Earth, then it doesn't matter which equation you use. Find the field strength caused by the Earth, find the field strength experienced by the board marker. It's the exact same thing. Doesn't matter. Now, you don't need to write this next thing down, but I do want to show you one other little thing. Okay, this equation, that first equation, looks an awful lot like Newton's law of universal gravitation, but it's not used to find force, it's used to find field. Look what happens if we combine these two equations. Okay, let's say, again, you get this board marker up here a certain distance from the Earth. The field that it experiences is the same as the field that's caused by the Earth because it's the same field. Therefore, those fields can be set equal to each other. Big G, m over r squared is equal to F over m. This m is the mass of the producer. This m is the mass of the experiencer. Let's rearrange that. Solve for F. Take the me up by multiplying. It becomes G times m of the producer times m of the experiencer over r squared. What is that? That's the gravity law, right? So if we combine the two field equations for the producer and the experiencer, then we get the equation that we've already seen 100 times before. Right, Aiden? Here's a table from your book, table 4.1. This is in chapter 4, and it's going to be near the beginning of chapter 4. It gives you the mass of all of these different bodies, different planets, the moon, the sun, and so on, and the equatorial radius. The equatorial radius is simply the radius of that planet from the center, or the whatever object it is, the sun, the planet, the moon, from the center to the surface at the equator. Okay. This will not be on your quiz tomorrow. Rather, I'll ask you to memorize all of these numbers for Monday's quiz. Okay? Don't worry, I won't ask all of you. I won't ask all of them. I'll only ask 3 of them. So you only have to remember 3 of them. Got that? All right, so you're not going to have a quiz on that, I promise. Okay, you won't. You have to refer back to that table in order to solve some of the problems we're going to do. We're not going to have a quiz on this on Monday anyways, probably not. But I'll let you know tomorrow for sure. If we do, you'll be given that table or at least any piece of data that you need off of it, okay? Okay, we're going to use that table now, though, to solve this problem, 4.5 on page 218. It says, find the magnitude of the gravitational acceleration of an object at the equator on the surface of the Earth and on the surface of the moon, and we want to find the ratio. Okay, Jace asked a question when we went over the homework. asked me to solve question number whatever it was. It said compare, which one was it? 6? Compare this to this, right? And we said when we want to compare, we divide. And we said when we want to find a ratio, we also divide. It's the same thing. That's what we're going to do here as well. We got to get G for the Earth. We got to get G for the Moon. Then we're going to divide them just like we divided my age to your age and got a ratio of 2. The gravitational acceleration of the object, gravitational acceleration all of a sudden. The gravitational field is the same thing as gravitational acceleration. Sometimes we don't call it acceleration anymore. We call it gravitational field because that acceleration is there, that field is there, whether there's something experiencing it or not. But you're not really accelerating if there's nothing there to experience it, right? Take it to another level. The board marker's there. What's its acceleration right now? 9.81? It's not accelerating at all. It's 0. But you would still say the acceleration of gravity is 9.81. It might make more sense to say the gravitational field strength is 9.81 than to say the gravitational acceleration is. So we want to find the field strength or the acceleration of an object at the equator of the surface of the Earth and the surface of the Moon. Let's say GE. It means the mass of the Earth here, which is 5.97 times 10 to the 24, divided by R, which is the equatorial radius of the Earth, which is 6.38 times 10 to the 6. Do that math, we get 9.7827. And the units for that would be newtons per kilogram. Hey, what's another set of units that we could use for that? You guys know this right now, right? Gravitational field strength is the same as acceleration due to gravity. Another set of units could be, right? Meters per second squared. Doesn't matter which one you use at this point. Okay, let's find the field strength caused by the Moon now. Gm over r squared. Same equation. Same number to start off as well. Let's use the mass of the Moon. 7.35 times 10 to the 22. And the equatorial radius of the Moon is 1.74 times 10 to the 6. Let's get that number now. We get 1.619. 3 newtons per kilogram. What do you do again if you want to find the ratio? 9.7827 divided by 1.6193. Divide them. Here we get 6. So the ratio is 6 to 1. That means that the field strength on the Earth is 6 times greater than the field strength on the Moon, meaning that you're going to feel 6 times lighter on the Moon. What's the quickest way to lose weight? Go to the Moon. Problem is, if you ever want to come back, you're going to gain that weight right back. You're not going to lose any mass either, by the way. It's just weight. Is that good? Okay, let's see what you can do with these 3 questions, please. By the way, question number 1, when they talk about 3R Earths, what does that mean? Yeah, 3 times the radius of the Earth. And the radius of the Earth we said was 6.38 times 10 to the 6. Okay, so let's see what we can do with those 3 questions, please.